A very good evening to everyone present here. My name is Rachna Palli, the Program Committee Chair of the IEEE Power Electronics Society Student Branch Chapter at New Horizon College of Engineering. I welcome all of you to our distinguished lecture seminar on Long Horizon Finite Control Set Model Predictive Control, Theory, Implementation, and Applications. Our speaker for today is Dr. Tobias Geyer. I would like to take this opportunity to introduce our distinguished speaker to the participants. Dr. Geyer received his diploma and PhD degrees in electrical engineering from ETH Zurich, Switzerland in 2000 and 2005 respectively, and the habilitation degree in power electronics from ETH Zurich in 2017. After his PhD, he spent 3 years at GE Global Research, Munich, Germany, 3 years at the University of Auckland, New Zealand, and 8 years at ABB's Corporate Research Center, Switzerland. There in 2016, he became a senior principal scientist for power conversion control. He was appointed as an extraordinary professor at Stellenbosch University, South Africa from 2017 to 2023. In 2020, he joined ABB's medium voltage drives business as an R&D platform manager of the ACS 6000/6080. He is the author of 35 patent families and the book Model Predictive Control of High Power Converters and Industrial Drives. He teaches a regular course on model predictive control at ETH Zurich. His research interests include medium voltage and low voltage drives, utility scale power converters, optimized pulse patterns, and model predictive control. Dr. Geyer is the recipient of the 2017 First Place Prize Paper Award in the Transactions of Power Electronics, the 2014 Third Place Prize Paper Award in the Transactions on Industry Applications, and of 2 prize paper awards at conferences. He is a former associate editor for the Transactions on Industry Applications from 2011 until 2014, and the Transactions on Power Electronics from 2013 to 2019. He is an International Program Committee Vice Chair of the IFAC Conference on Nonlinear Model Predictive Control in Madison, Wisconsin, USA in 2018. Dr. Geyer is a distinguished lecturer of the Power Electronics Society in the years 2020 and 2021. Before we continue, I request the participants to keep their mics muted during the session. You can unmute or post your questions in the chat box at the end of the lecture. Participants are also requested to fill the feedback form, which will be shared at the end of the lecture. On behalf of the IEEE PELS Student Branch Chapter at New Horizon College of Engineering, we warmly welcome you, sir. Thank you.
Thank you very much for the kind introduction. Maybe enable the screen sharing for me, then I can start the slides. So it's a pleasure to be able to talk to you today. It's an honor for this possibility. Thank you very much. And the topic today is long horizon finite control set model predictive control. Some people also call it direct model predictive control, but what I'm trying to show you is how we can formulate and solve the long horizon control problems. So I have 1.5 hours to talk. So this is quite a long time. So I prepared a bit more material than usually, but I will try to go through it in a bit more detail. So I will have a bit of a slower pace and try to explain to you the details rather than showing you a lot of slides and quickly browsing through it. So I will try to make good use of that time. And if you have any urgent questions, maybe you can also put them in the chat, and I will try to monitor the chat, and then if it fits, I will try to directly reply to it while walking you through the slides. So also thanks a lot for the kind introduction. So as you have seen, I'm sort of a hybrid person. So during the day, I work in industry. I'm exposed to industrial problems, but during the evenings and the weekends, I'm more of an academic. So I'm interested in the more pure research aspects, and things that are not necessarily going to be used within the next 2 or 3 years. So today I want to give you an introduction. What is control and modulation? How do we typically do control and modulation for power electronics? And then introduce this concept of model predictive control to you. What are the key features? What is the control principle? How is that usually done? And then look into this finite control set MPC in detail. And I will start in a simple way by looking at the horizon of one step. And that's typically solved by trying out all the solutions, called enumeration. And I guess many of you might have even worked with that. It's a fairly easy and straightforward concept. But then I want to nudge you towards longer horizon. I want to show to you how we can formulate these problems, and more importantly, how we can solve them efficiently. And in doing so, we will formulate a branch and bound solver, so a method that sort of does a divide and conquer, splits the big problem into smaller problems, but does not need to solve all the smaller problems, but rather we can come up with certificates that certain parts of the solution can't be in certain parts of this search tree. And then we will look into performance. We will see that the longer horizons do give you a better performance, but I want to show you also for what sort of problems they have a benefit. In some cases, short horizons are good enough. And then in the end, formulate some guidelines and give you some tips, some hints, maybe what to do and maybe what not to do. And then sum up with summary on conclusions. Now, in terms of introduction, I'm interested in medium voltage drives predominantly. That means 3-level converters, 3-phase obviously, but this is a neutral point clamp converter driving an induction machine. But the principle, the methods, they directly apply also to 2-level converters. So I will also show you examples where we have just a 2-level converter. And obviously you can use that for machines, but you can also use that for any other load you have, say a grid. And these sort of problems are, I would say, relatively easy. We just want to control the current, the stator current in this case, along references, and we don't want to switch too much. We want to minimize the switching frequency. So it's a system of first order with a problem in the alpha axis and one in the beta axis, so 2 orthogonal problems. Short horizons are often good enough. Long horizons help a little bit. Maybe more interesting are problems that are a little bit more complicated. Problems where you put a filter, a sine filter, an LC filter between your converter and your machine. You can also think here of having maybe a transformer. You would have the transformer impedance and then a point of common coupling would be an equivalent problem. And here you need to control 3 quantities in alpha, beta, not just one quantity. So this is a more complicated problem and also more interesting. And here we will see that long horizons really do make a huge difference. So they lead to an improvement of a factor of 10, so order of magnitude, compared to a horizon of 1. Now, the way we usually formulate and solve these control problems is we say we have an inner current loop. So this could be that is typically formulated in a rotating coordinate system. Let's call it DQ. So we need to know the angle of a rotating coordinate system. So we would have a D-axis and we would have a Q-axis. And this would be rotating at a certain angular speed, omega frame. And that turns AC quantities into DC quantities. So that means here we have sinusoidal quantities. That's a bit awkward to control, to track. But here we have DC quantities. And these DC quantities we want to bring towards their references. References would have a star. So this is always, in my nomenclature, a reference. And then we have here a current controller working in DQ with 2 components. And usually we have one for the d-axis and one for the q-axis, and then there's some cross-coupling, some decoupling with some feed-forward terms. And that gives you a voltage reference in dq, which we translate back into ABC, into the three phases. And then we have a modulator, pulse width modulation, that translates this into switch position. So these would be the switching signals in the phases A, B, and C. So I'm using the Anglo-Saxon notation. U means switch position, V means voltage, and not U is not a voltage. It's a switch position. Now the beauty with this control problem formulation is that the current controller does not know that it controls a switching power converter. So when we sample the currents, when the current ripple is 0, then the current controller will not know that it's actually controlling a power converter via a modulator. It assumes it's a linear system. So the switching characteristic is hidden from the controller. So this makes the controller design, I would say, relatively easy, relatively straightforward, but you also pay a price in the sense that because it is hidden, the switching characteristic from the controller clearly doesn't know about it, and it can't interact, it can't improve it. So the switching ripple is given by the switching frequency of the modulator and the type of modulator used. Now the way we do it is we typically formulate the current control problem in a rotating or field-oriented control framework. So I've indicated already up here, but you have the same down here. And on the machine side, we would have a rotor flux, and the d-axis is aligned with that rotor flux. And then we have a magnetizing current that magnetizes the machine. And we have a torque producing current that produces torque. And you can have these current controllers as a proportional integral controller, or you can go for deadbeat. Now, in terms of modulator, typically we would use carrier-based pulse width modulation. So we would have, in case of a 3-level converter, we would have an upper carrier, triangular shaped, and the lower carrier, triangular shaped between -1 and 1. We would have a reference signal, this modulating signal, that would be this modulating signal here. This we would feed in here. And whenever we have an intersection with natural sampling, we would have a switching transition. Now, space vector modulation is similar. We just don't have carriers, but we sort of analytically compute the on and off times for the respective voltage vectors. Or we could go for discontinuous PWM, where we would maybe freeze the switching here when the current, let's assume power factor 1, when the current and the voltage is high, and we would also freeze switching here. So one phase would be frozen and the other 2 phases would be switching. You get lower switching losses, but you pay a bit of a price in terms of harmonic distortions. And then there's programmed modulation. So most notably, they're optimized pulse patterns. That means we have a very different approach. We say we have a modulating signal. We have a modulation index, sort of an amplitude of the voltage we would like to create. But we then say we have a certain number of switching angles, let's say 3 over the first 90 degrees. And then we ask ourselves, what is the optimal position of these 3 switching angles so that we minimize the harmonic current distortions. So we compute with an optimization problem the position of these 3 switching angles so that we minimize the harmonic current distortions for this given modulation index. And we then assume symmetry. So we say that whatever we do in the first 90 degrees, we mirror at 90 degrees and then repeat in the second 90 degrees, and then we have point symmetry here. Or you can use selective harmonic elimination, where you set a certain number of low frequency harmonics to 0. And then, and that's more rarely, a bit seldomly used, is you could try to combine the control and the modulation in one state. And one example would be direct torque control or direct power control. So control and modulation is done in one entity. You don't split it up into a linear controller with a modulator. Very good. And then there is model predictive control, which is fundamentally different. So the idea of this way of thinking of MPC is that you say, I have a certain mathematical model of my system, of my converter, of my load. And with that system, I can predict how the system will evolve in the future over a certain time horizon by taking into account constraints. We will talk in a moment about constraints. And then we choose the best control input, and we will have to define what best is. Best means it is best in terms of an objective function. And we find that by solving an optimization problem numerically, so iteratively, not analytically, not by solving a set of equations, but by doing that step by step. And this we redo at the next time step with new measurements over a receding or shifting horizon. So let's go through each of these elements one by one. So the first one is that we have this internal model, and this model describes the system behavior. So in the simplest case, we would have certain state variables. So this could be currents, or that could be fluxes, or that could be voltages over capacitors. We have the inputs, so that's our switching, our three-phase switching signals. And based on that, we can compute what are these state variables going to be at the next time step. So we do work in a discrete time domain. So that means we are at a certain state or certain outputs and a given certain input that we apply for the sampling interval in the sampling period. We can make a prediction what the states and the outputs are going to be at the next time step. And then we have an equation that maps states to outputs. And this can be linear, or in this case, generally nonlinear. So this allows us to look into the future, to make predictions, and in a way, it makes the controller smart. The second ingredient, which is, I would say, is the distinguishing feature of MPC, is that we can impose constraints. We can say we have a certain current, let's say current as a function of the time, and we want this current to be below a certain maximum current. And this could indicate an upper bound so that we can ensure safe operation of the drive. So maybe at this point here, we would have a trip level. We would have to have an emergency shutdown of our converter. So we want to make sure we don't have this. So we impose this here as a constraint so that we avoid trips. And then maybe somewhere up here, we would have some destructive things going on. We might damage our converter. So these constraints, they can be imposed on states, on inputs, and on outputs. And this is done while designing the controller. So during the synthesis, it's not done afterwards, like when you add an anti-wind up to your controller. This is done during the design. Then we have a cost function. That's effectively something that maps our objectives. So what would we like to achieve into a number? So the cost function just tells us, so this is a number, so it's a real valued number. It just tells us how good we achieve what we want to do. And terms could be, for example, the tracking error. So how much does the current deviate from the reference of the current at certain time steps in the future? And we might say that a small deviation, a small error here is penalized very little, so almost not at all. But a large error, we could say, is penalized a lot. So this is a sort of quadratic cost function. We don't care much about small errors, but we really want to avoid the big ones. And then we have this term here, which effectively tells us that the changes in the switch positions, which is the switching frequency in a way, should also be small. So this does the tuning of the controller. So we might have to tune this lambda here. And then there is numerical optimization. So in general, we are not able to analytically, in the form of equations, come up with a control law. We need to solve it step by step. That means we have a certain feasible set, a certain input space that is defined by our constraints. And we want to find the sequence of input variables we would apply to our system so that the cost function that tells us how well we meet the objectives is minimum. So these ones here are level sets of our cost function. The closer we are to this point, the lower the cost. So the better it is. And we might start somewhere here and then move step by step orthogonally to this level set till we hit this constraint here, the bound of the feasible region. And then we know that this, if certain properties are fulfilled, in this case it's convexity, that is then the optimal switching sequence. And then we do this. So we formulate our problem over a certain horizon. Let's say we look 5 steps ahead or 6 steps. We compute the switching sequence or the sequence of manipulated variables over this horizon. But out of this long sequence, we only implement the very first element. So only the first element is given on our converter. And then at the next time step k+1, we make new measurements. We make new estimates, and we redo the whole thing over a shifted or receding horizon. So you might say this doesn't make much sense. I mean, why don't I use all the rest of the control sequence? And the reason is simple. If you did that, if you applied the whole sequence, you will only be able to act again here. So if a disturbance or something happens at this point here, you're not able to react. You have to wait till here. But with this receding horizon policy, if the disturbance happens here, you will be able to act already at the next time step. And you will see the effect this disturbance has caused by measuring or estimating the states. Then you say, why should I look so far ahead into the future if I don't really use that and only implement the first element? Yeah, that's all about having a good plan, to having a good strategy and then implementing the first element. And I'm trying to convince you, and I will try to explain to you in which cases it makes a difference to have a long horizons. And in some cases, you will see it also makes very little difference. In the way, it is a bit like playing chess. If you just look one step ahead, you might struggle to beat your opponent. But if you look 2 or 3 steps ahead and you have a nice strategy and you adapt it depending on how your opponent acts, you might be actually able to beat them. So this receding horizon policy that adds feedback, so that's the difference between open loop control, where you apply the whole thing in an open loop fashion. So here you apply the first element, so this is closed loop control, giving you feedback. And that really gives you robustness. So if your parameters are not perfect in your model, if your model is not perfect, if you have disturbances, you will be robust to these disturbances. You will be able to counteract them. Okay, so that's the basic philosophy of MPC. Now, this MPC, model predictive control, that's an old concept. And it comes from industry and not from academia. It was developed in the process industry. So people doing chemicals, refining, pulp and paper, and so on. And then academia picked it up and made it, a sound framework, a theoretically sound framework with a nice, solid foundation. But already in the in 1999, there were more than 4,500 applications reported in this paper here. So this concept is an old concept. Only recently, a few years ago, has the power electronics community discovered the benefits and started using it and adopting it. Main reason maybe is that the sampling intervals, they were really long here. They were in the range of minutes tens of minutes, in some cases even half an hour. And here we're talking in the automotive, air and space industry, we're talking about tens or hundreds of milliseconds, and power electronics is in the range of a couple of microseconds. So we needed a tremendous speed up in computation time. So when you then ask yourself how many publications there are on predictive control, so you can go to IEEE Explorer, for example, and you can look at the number of publications per year. And what I did is I just put in a search string where I say I want to have papers in the abstract or the title with predictive and control and inverter or converter. And then you see you get just 1 or 2 or 3 publications. And then sort of from the year 2000, it started taking off. And since then we have seen an exponential growth. So that's the equation that sort of matches the measured number of new publications per year from IEEE Explorer. So Joachim Holz, he had some early publications. He would not call it model predictive control, but many of the ingredients, they are available in his paper. Then Ralph Kennel, he looked into generalized predictive control, but I would think things really started to become exponential, to take off with the proposal of this finite control set MPC, or one-step predictive control by Jose Rodriguez in 2004. Then we have been having symposia precede, and also some first pilots, some first products in industry. So they have nothing to do with finite control set MPC. This predictive control of load commutated inverter drives is a very, very different method. Effectively, we control the rectifier and the inverter in one shot, and we directly manipulate the firing angles of the thyristor bridges. And then there is model predictive pulse pattern control, which is a product. That's the second predictive control product in industry. Again, that has nothing to do with finite control set MPC. Rather, it is based on optimized pulse patterns. So these optimized pulse patterns are pre-computed, and then they are tweaked online by modifying the switching instances. That's model predictive pulse pattern control. So then we need to look a little bit at nomenclature. We have direct control methods. So we have methods where we have a controller that directly manipulates the switch position. So this U here would be the switch position. So there is no modulator. The modulation stage is included in the controller. And we will talk about that today. That's this reference tracking, this finite control set MPC. But also this MP3C using optimized pulse patterns would be a direct controller, or when you have bounds, when you say I have upper and lower bounds, and I want to keep my torque and my state of flux magnitude between these bounds, that is also direct MPC. And then there's indirect MPC. That means we put a modulator between a voltage reference or a modulating signal, and this modulator comes up with the switch positions. So this is rarely used, maybe because people feel that solving these quadratic programs is maybe a bit cumbersome. So I would think that the mainstream, the main focus is on this finite control set MPC. And that's what we are going to talk about today. Good, so let's start with the simple version of finite control set MPC with a horizon of one step. And again, we look into this case study, this 3-level, this neutral point clamped inverter driving this induction machine. But 2-level inverter and any other machine would be equally fine. And the problem is that we want this current, the stator current that we measure, we want it to follow its reference, that would be sinusoidal reference at steady state, by manipulating the switch positions in the 3 phases in A, B, C. So we need to make here a choice of -1, 0, and 1 in the 3 phases. And we don't want to switch too much, particularly not for these high power converters. So the way to do it is we simply say, I want to map what I want to achieve into a cost function. And what I want to achieve, I want my currents to follow their references. So I penalize the predicted deviation of the currents at the next time step. We are time step k. The next time step is time step k plus 1. This deviation from the reference is penalized. And you might ask yourself what this squared 2 norm is. That really just means if you have here a variable xi, let's say in alpha beta, and you take the squared 2 norm, that means you have xi in alpha and xi in beta. And you take the squared 2 norm, and that means you take the first component squared plus the second component squared. That's all it does. I'm not sure why my tablet produces these horizontal lines. I'm sorry, they're not meant to be there. So we want to get the tracking error small, and we want to switch little. And switching means between the previously applied switch position and the switch position we're choosing now, we want to have as small a difference. So that means when we reapply the same switch position, this would be 0. If we switch in one phase, this would be 1 times lambda u. If we switch in 2 phases, this would be 2 times lambda u. And you see already we need to come up with a lambda. That is the trade-off between good tracking and low switching. And in general, you can't have both. So we need to come up with a good lambda. Now the system model, you can pick any model, any load, any converter you want to pick. In this case, I assumed it to be linear, but it does not need to be linear. So it's a simple state space model. So given the states now and the input now, we can predict what the states at the next time step will be. Could be currents, could be fluxes, could be capacitor voltages, and so on. Then we have a constraint set. So the switch position here belongs to a finite set. In this case, with a 3-level converter, it's -1, 0, and 1. If you had a 2-level converter, it would be simply -1 and 1. And 3 means we have 3 phases, so phase A, B, and C. And then that's a peculiarity of the 3-level converter, the neutral point clamp converter. You must not switch from A1 to a -1. That might damage your converter. So this is not allowed. You first must go via the 0, and then you may switch to the -1. And this constraint, this complicating constraint, expresses that in each phase, no more than switching by 1 step up and down. So that's the problem formulation. So we want to minimize this cost function so that the system model is fulfilled while meeting these input constraints. So we want to get good tracking, and we want to have an acceptable switching or modest switching frequency. And whatever that means, I mean, that's really problem specific. So at time step k, where we are right now, we will compute the optimal manipulated variable, the optimal switch position, by saying we have previously applied a certain switch position. If we have applied this one, then there is a certain set of switch positions we may apply now. So if in the previous step, so let's just look at one phase, in the previous step you have applied a -1, then at time step k, you might only apply a -1 or a 0. You may not apply a +1. This you have to do in all 3 phases. So we have the set of allowed or admissible switch positions. And then for each tentative switch position now, we can make a prediction. We can predict what's the current going to be like after one time step if we use that very simple model. And that very simple model simply says, given the current now and the rotor flux now and the switch position now, we can predict what the current is going to be like after one time step. So we are effectively here at time step k. We have a certain current. We are here, and we can predict for different switch positions where these currents are going to be like after one time step. And then we apply the cost function. We just say we put in this predicted current into our cost function like this. We put in the switch position, so we get this penalty on switching, and then we get here a number. I will have for you an example in a moment, and then we pick the cost function value that is the smallest and the associated switch position. And this is what we would say would be optimal. So optimal means with respect to a cost function. So U would be optimal with respect to this cost function here. Now, let's look at a simple example, and maybe we look just at the top part, the alpha component. Down here you have the beta component. The control problem is usually formulated in alpha beta, rarely in DQ, because there's no real benefit of doing it in DQ. I mean, we can nicely track sinusoidal time-varying quantities. DQ is not really needed. So we predict for the given current we have measured at time step k. We go through all the different combinations of allowed switch positions, and we predict what is the current going to be like after one time step in alpha and in beta. And then we apply this cost function. And the cost function simply says, what is the error? So the deviation between the predicted current and its reference in alpha and in beta. You remember this is the square 2 norm, and the penalty on switching. So let's quickly walk through this. I mean, here, this choice here would mean we apply this 1 minus 1 0 again, which we had previously applied. So this is the same as at time step k minus 1. So there is no switching. There's no penalty on switching. But you see the error is relatively large. So this is quite a relatively high number. Okay, we could say we switch to this 1 minus 1, 1. So we have a much smaller error. This is reflected here. The error gets much smaller, but we now have a penalty on switching. Or you say, I switch twice, and I apply this switch position here, which is the same as this one here. But that's maybe not such a great idea because the tracking is worse and I have to switch twice. So we will not be using the third option. That's never going to be a good choice. But should we now pick the first one or the second one? Should we switch or should we not switch? And we can't answer it. I mean, it depends on your penalty on switching. If your penalty on switching is huge, if it's a large number, a large positive number, then you don't want to switch because the price you would pay here for switching would be huge. You better don't switch, and you have this, somehow pronounced ripple. If, however, lambda u is more or less 0, then the cost on switching is more or less 0. And then you really benefit from getting your tracking errors more. So then you would switch. So you see that this lambda, that's really your tuning parameter. You really have to weigh what is more important for you. Tracking, so how small the current ripple is going to be, or the control effort, so your switching frequency. So in general, and we will see that later on, if you take here the switching frequency and here the, let's say, the current distortions, the current THD or the current ripple, that you get such a trade-off curve. So you can have a low switching frequency and a high THD, or you can have a high switching frequency and a low THD. And this sweet spot that we feel is optimal or tolerable or good enough, that's going to be set by this lambda u. Okay. And if you do that, and if you apply that to this machine, then you will get these simulation results. So you see, well, I should explain, I work here in a per unit system. So all variables are normalized with respect to their peak value. So at rated operation, at nominal speed and rated torque, the currents would have an amplitude of 1. So also in the per unit system. So the dashed dotted lines are the references, phase A, B, and C. And the actual currents have this ripple on top. We can compute using a fast Fourier transformation. We can compute the harmonic spectrum. So you would see here the fundamental component that would be F1 equal to 50 Hertz. It would have an amplitude of 1. But then this harmonic spectrum of the currents looks a bit weird. It is, you don't have distinctive classic harmonics as with pulse width modulation. You have some noise, and then you have maybe here an 11th harmonic. I believe this is a 13th harmonic. But this almost looks like a 14th harmonic, an even order harmonic. And the reason simply is there is no symmetry in your switching pattern. There's no symmetry within the phase and no symmetry between the phases. Hence, there is no symmetry in the current ripple, and hence you don't get sharp, distinct harmonics in your harmonic spectrum. So this is a feature of finite control set MPC, because we don't have a modulator. We do modulation in an ad hoc way. We don't get this sharp classic pulse width modulation spectrum. Nevertheless, what works really well are torque steps. So we have here torque step from full torque to zero torque and back from zero torque to full torque. We call this is an induction machine, so we need a bit of magnetizing current even at zero torque. And you see you get a very, very fast response within a millisecond or so. Here it's slow, but here we are operating at high speed, so we need to move the stator flux forward, and we don't have enough voltage. I mean, our DC link is limited. So hence it is slow here, but here it's extremely fast. Now we can look into a little animation. So you see here the currents, the stator currents in alpha beta versus the time. We are here at the current time step, let's call this K, and this would be K plus 1, so on, looking into the future. So everything here to the right would be a prediction, and everything to the left would be the past. You have here your torque, and you have here your switch positions UA in phase A, in phase B, and in phase C. And that torque step is there to be applied. Should be coming up now. Now the torque is being ramped down. That happens very quickly. We're at zero torque, and then the torque step back upwards comes, and that is a bit slower because of the lack of voltage margin. But you see already the prediction horizon is so short that it's actually a bit of a surprise that this works well. Now, summary horizon 1. Prediction horizon is 1. We use a load or a machine model. We use a converter model. This lambda u provides a trade-off between tracking and switching. It is very simple, both from a concept point of view as well as computationally, because you just try out all the different possible options you have. It is extremely versatile, so you can use it for any problem, any topology, any control objective you have. But it doesn't work in some cases so well. So its performance in general is fairly average. In many cases, it is worse than classic modulation using carrier-based pulse width modulation. So we need something better. And the something better is finite control set MPC with long horizons. So let's look into these long horizons. And first, let's understand why it's difficult to have a long horizon. So we have the same problem formulation here. We want to track these measured stator currents and move them along their references and directly manipulate the switch positions. So we do that in alpha and in beta over the time axis. And let's assume we are at these points here. Now, if you just look one step forward, so we have a horizon of 1, and we have this 3-level converter in 3 phases. We have 3 to the power of 3, 27 different combinations. This we can easily handle, we can try them all out. But if we go for a horizon of 2, we have 27 to the power of 2, so we have 700 combinations. Maybe we can try that out, maybe not. Horizon of 3 gives us 20,000. So we get this combinatorial explosion. So we have 27 to the power of n, where n is the length of the prediction horizon combination. Okay, you say, I'm interested in 2-level converters, then you would have 8 to the power of n. It's almost as bad. So this is hopeless. So it's a hard to solve optimization problem. I mean, you have an exponential increase in the computational complexity as you increase the length of the horizon. So enumeration is difficult. Enumeration is not easy. Trying out all the possible solutions actually leads to a very difficult optimization problem. Unless you have a horizon of 1, then it's very easy. So we can apply heuristics. So we can try to apply in an ad hoc manner the number of switching sequences we have to explore. There are different ways to do it. You could say, I'm happy with a horizon of 2. I could only consider switch positions that refer to voltage vectors that are close to an ideal one. So I could say that I have in alpha and in beta, I might have such a hexagon of voltage vectors. And somehow I determined that I'm in this modulation region in this little triangle. So ideally, I would like to be here. You could say, then I just need to look at this one, that one, and that one. You can do that. You can try to have some hierarchy. You can try to minimize first one part of the cost function, then another one. But in general, there are no guarantees that this problem can be solved. And there's certainly no guarantee that this is done well. And well means optimality. So you will give up optimality and you don't really know what you get. And it's easy to construct counterexamples. So for each one of these methods, you can create a case where you can actually show that this idea is really bad, even though in general they might work. So the question is there a better method? Is there a method to solve the long horizon finite control set MPC problem where I have a guarantee of optimality and I have a low computational burden? And the answer is yes, as you can imagine. And it's called sphere decoding. It's a branch and bound method, and I will now present this to you. There's one little problem or one little footnote, and that is the prediction model is required to be linear. So you need to have a linear state space representation with matrices A, B, and C. You can't just have here a nonlinear term. So that is a restriction. I would say it's a significant restriction. But if it is linear, or you can formulate it as a linear problem, then there's sphere decoding. So let's formulate these long horizon MPC problems. And let's ask ourselves first, are our problems more linear or are they more nonlinear? So is that really a problem that we have a linear system representation? So pick a system. I would say these components in here, they are effectively linear. The inductor is more or less linear. The capacitor is linear. Maybe there is some saturation of magnetic material. Maybe the torque is nonlinear. But the majority is really, it is mostly a linear system. we have multiple inputs, multiple outputs. So you have your switch position in phase A, B, and C, and you want to control here currents and voltages and currents or fluxes. So a MIMO, multiple input, multiple output system. MPC can handle that well. The main nonlinearity we have is the actuation. So these switch positions, these on-off, this 1, 0, and -1. That is our nonlinearity. At least I would claim that. So it's a nonlinear system or mildly nonlinear system with integer inputs. It is accurately known. We do know our system. Maybe not when we are grid connected, then we have to maybe estimate the grid impedance. But in general, we have built this filter, we have built this machine, we have a fairly good understanding. Typically, we have less than 10 state variables, and typically we have 3 variables we manipulate to achieve our control objectives. Keep in mind, this MPC comes from process industries. So big distillation columns. So there, the system is not accurately known. What people do there with distillation columns, they apply inputs. They have outputs, let's say 10 inputs, 10 outputs. And what they do is they apply a step to one input. And then they measure, how do these outputs react? And then they do this for all the inputs and for all the outputs, and they try to come up with a model. That's how MPC evolved. And you don't have just 10 state variables, you have hundreds of thousands. So highly unknown models with lots and lots and lots of state variables. In contrast, we have almost a heavenly, a blissful situation with just a few states and a fairly well-known, almost linear model, except for the on-off characteristic. So what we do is we do these predictions. We say we work with the discrete time axis, and we have our state space system. So we say we have a certain state, we have measured it. Let's take a tentative input. So this notation means U of k. So this is just a more compact notation. This is the switch position at time step k. This is the state at time step k. So given this input, I can make a prediction what my states are going to be. And these are always vectors in general, not just one component, but 10 or so. What the states are going to be after one time step. At the next step, I can ask myself, if I have now predicted the state and I'm going to apply the switch position, I can make a prediction what the next vector of state variables is going to be like. And then I can put in the previous prediction into this one here. And then I can get the mapping from the initial state to the state at time step k plus 2 using switching at time step k and k plus 1. And this I can repeat. So given my inputs, which I have to choose, which I will optimize over, I can make a prediction what future states are going to and if you have the states, you can also compute what the outputs are going to be like. So the outputs are then simple linear combinations of the states. Okay. Now it's important to understand how you can model and how you can predict the future. Then we want to see how do we choose these switching sequences? What is optimal? And for this, we need a cost function. So the cost function maps what we want to achieve into a number, into a scalar, into this J. And commonly used cost function terms could be the deviation of the predicted current from its reference, let's say at the next time step. And that is a simple, there's a simple physical underpinning under it. So this is here in alpha beta, but in general, what you want in the A axis, you want as small a current ripple as possible. In the B axis, you want as small a current error. And in the C axis, you also want to have a small current error. And you can show very, and you can show very easily that you can, that minimizing the current error A, B, and C is the same as this cost function. Well, maybe if you don't mind, hello, could you mute your mic, please?
Naman Singhal, can you mute yourself? Naman Singhal, can you mute your audio?
बताने वाला हूँ, तो वीडियो को अगर आप चाहे बीजेएमआई वाले हो या पुष्टि वाले दोनों भी देख सकते हो। तो चलो सबसे पहले तो अभी मेरा जो वर्जन है 1.8 है और विदाउट वीपीएन वाला है। तो सबसे पहले तो अपन यहाँ पर इसे
sorry for the inconvenience.
No problem. So we want to get the ripple in phase A, B, and C small. And this directly leads to this type of cost function. So you get sort of these concentric level set. So you want to get the deviation in alpha beta from the reference as small as possible. So this minimizes your current THD in the currents. You could also say, I'm interested in the torque. So I want to follow a torque reference, or I want to follow a state of flux magnitude reference. So this could be a direct torque and flux control. This could be a direct current control. And then you want to get your switching effort small. This we have discussed already. So you need this penalty. You need this penalty on switching. Maybe coming up with a good cost function is not so easy, but usually we have some, you can base it on physics. I mean, you can start with a THD, or you can say, I want to have good torque and flux magnitude tracking, for example. So if we put this all together and we want to have this long horizon finite control set MPC, we say we have a discrete time linear system, time invariant, so it doesn't change with time, and it has integer inputs. So these switch positions here, they are integers. So Z is the set of integers, and there is no modulator. We have this cost function. So the tracking error is being minimized and the control effort. Now you might wonder about this strange nomenclature here. It just means I was a bit lazy. It's just this Q matrix which penalizes the deviation, and the quadratic term or quadratic form is here in the center. So the normal way would be to write it like this, but this is a more compact representation. And then we have the input constraints. So this could be here phase A, this could be phase B, and then phase C, and so on. And then the same at time step 1, 2, and 3. And then we put everything together into one big optimization problem. So the cost function on top over the horizon and the system model, the switching constraints, and that we can't switch between -1 and 1. And then we minimize it. And we try to compute the sequence of manipulated variables. So this the switching sequence. So effectively, that's what we're going to be applying to our converter. And now it gets difficult, because how are we going to solve this? In general, this is an easy to solve problem, but this U, the decision variable, the optimization variable, has integers. So this is a very difficult problem to solve. So we need to apply a few tricks, and it takes a few days to derive this equation, hence I don't do it. I just want to maybe refer to this paper and explain to you what this equation means. But you can take this set of equations, this optimization problem, and rewrite it in this form. Now, what these equations mean, these components, is we still have the switching sequence here, this U. This is what we want to find. we have the so-called unconstrained solution. So U unconstrained, this is a real valued number of the dimension 3 times the length of the horizon. So this is an integer and this is real valued. So if we had a modulator, this is what we would be applying. This is sort of akin to a modulating signal. And that depends on the current states, the previous switch position, and the references in the future. And then we have this matrix V. V is the so-called generator matrix. It's a sort of a square root. You get it by doing the Cholesky decomposition of the so-called Hessian matrix H. H is the main quadratic matrix in your optimization problem, the so-called Hessian matrix. So this is a bit technical, but what you're after is you want to find the switching sequence so that you minimize the distance to the unconstrained solution, which you can compute easily, in the space created by the generator matrix. And hence it's called generator matrix because it generates a space in which you work. Now this sounds complicated. It's actually not so complicated. What you have here is phase A, the switch positions. So you have a 3-level converter. In phase A, you can have a -1, a 0, or a 1. In phase B, you can have a -1, a 0, and a 1. Phase C would be coming out of the plane. And we can transform that using this generator matrix, which is effectively, in our case, diagonal with some little sub-diagonal part. You can transform it into this sort of tilted or skewed lattice or crystal. So these points here, they are the same, they're just slightly deformed. And in this new space, we want to solve this optimization problem. So we want to find the integer point in this distorted crystal that has minimum distance to the unconstrained, this U unconstrained solution. So that means if we compute this unconstrained solution and we round it, we take an integer variable that is nearby, we compute the radius of that circle. And now we know, because we want to minimize the distance in this space, that we have to find a point that is at least as close. So we have this problem here. We have found already one point by rounding the solution, and we want to have the minimum distance. So this is this Euclidean distance. So it has to be minimum distance. And then we can look at the points that are within that circle or sphere in general and find the one that is closest. Now, that is comparatively easy. We will try them out with some with a nice method, but we don't need to look at these points here anymore. So we know a priori that they are much further away and they can't be related to the optimal solution. And this provides a very tight bounding. Now, how do we do it? Let's consider a horizon of 2 steps and 3 phases. So we have a switching sequence with 6 elements. So we need to find a time step. We need to find a time step K. We need to find a switch position in phase A, phase B, and phase C, and then time step K plus 1 in phase A, in phase B, and in phase C. So we start here and we ask ourselves, should we apply a -1, a 0, or a +1? And let's assume the -1 is already outside. Let's assume the -1 leads to such a choice. So we know from the beginning that this is the cost is too high, so we don't need to further consider it. Maybe the 0 is inside, and then we go into phase B and so on. So we will very quickly end up with a possible switching sequence. We don't know yet if it's optimal, so we need to look at the rest of the search tree by moving back upwards, and maybe there is also one part of a search tree we need to explore. But in general, we only need to look at one or at two branches till the bottom. So whenever this radius rho is exceeded, we have a certificate, we have a proof that the solution can be attached down here. So here's also a big search tree. So each one branches up in 3. I mean, there are hundreds of nodes attached to it. And we have a proof that we don't need to look further into this one here because it will only get worse. This cost is additive. If the first element is outside, we will only make things worse. These are squares. So we have a certificate. And whenever we find a possible solution, we can tighten the sphere. So this method is extremely, surprisingly powerful and effective. And you see that here for a horizon of 10 and 3 phases, we have 30 elements. That in the majority, in 80% of the cases, we find the optimal solution after having explored 30 nodes. So the minimum. So just, I mean, we effectively walk down and we have found an optimal solution, and we have the proof that this is the optimal solution. And then there is a bit of a tail. Sometimes it takes a little bit longer, but you could also cut off this tail and say, I accept a certain degree of suboptimality. So this is very effective, and it's very difficult to make it any faster because in most cases, you find the solution already in the minimum number of iterations required. So the sphere is very tight. And you also see it here when you do this prediction horizon and you use the classic exhaustive search. So for a horizon of 1, we would typically need to look at 18 elements, not at 27, some are not allowed. Horizon of 2 might be 340, 3, 5,000, 5, a million, and then I was not able to compute things anymore. But with this sphere decoding, it's just a few. So you get a tremendous reduction in number of nodes, so a tremendous reduction in computation time. So how does that look like when you use it? So this is an example with a horizon of 40. So we have 27 to the power of 40 combinations. So that's maybe something like 10 to the power of 80 combinations that we can solve here in a couple of tens of microseconds. You see here we are time step 0. So we have sampling interval, t-sampling interval of 25 microseconds. We have 40 steps. So the length of the prediction horizon is 1 millisecond. And you see this receding horizon policy in action. Effectively, it is nicely moving through. Because of the switching, every now and then we have a discontinuity. We add a switching transition or we remove one, but largely you see it nicely moving through. Now, these number of combinations, this 10 to the power of 80, that's the number of atoms in the observable universe. So that's an incredibly, incredibly high number. So it's absolutely impossible to try that all out. But with the sphere decoding, we have proof that we have found the optimal solution by just exploring a few tens of those choices. Now, if you apply that to induction machines, like this example we have had previously, and we have here the tracking of the current, you compare it with the state of the art, in this case, let's say space vector modulation. So omega means nominal speed. So let's say 50 hertz fundamental frequency, nominal torque, switching frequency of 250 hertz. You see this carrier-based or the space vector modulation that doesn't look so good. I mean, the current THD is quite bad. The harmonics are huge. These are sidebands, but the carrier frequency is at 450 hertz. So it would be here. So these would be sidebands, but it's hard to distinguish them. You can go for optimized pulse patterns. You can almost halve the current THD while having the same switching frequency. So we just switch in a bit of a smarter way, and it has a tremendous impact on the current ripple. Or you can go for this finite control set MPC. And this is a surprise. You get a current THD of 6%. So rather than 7.7, you bring it down to 6% at the same switching frequency. And if you go for a longer horizon, let's say 10 steps, you end up with a horizon of 10 and a current THD of 5% at the same switching frequency. So you do get a benefit. And what you will see here is that the switching becomes more regular. You have a bit more symmetry. So here you see you have a lot of switching and then nothing at all. So here it's nicely distributed, and the harmonics become cleaner. They look a bit more what carrier-based pulse width modulation would provide. So these ones I will maybe skip in the interest of time, but I will effectively want to tell you is that tuning is a bit tricky because you have two things you need to tune. You need to tune the penalty on switching, the lambda u, and you need to tune the sampling interval. Both are effectively parameters. And if you just do Monte Carlo simulations with a horizon of 1, you're typically worse than space vector modulation. You need a horizon of 10 to be as good as space vector modulation. And the benefit you would get when you operate at a low ratio between switching frequency and fundamental frequency. So a low pulse number. Then this method would work well. At high switching frequencies, so where you would usually use it for low voltage converters, it doesn't really work well. It doesn't perform well in terms of THD per switching frequency. Now, a question often comes up, torque steps. Do long horizons reduce or increase the length of the transient for torque steps? And the answer is they have no impact. I mean, having a long horizon has virtually no impact on the torque step. It looks exactly the same. I mean, you can see I did not copy paste it. There are some small variations, but the speed is the same. So the settling times is not influenced by the length of the horizon for this first order system where we just have a machine. So let's then move on and let's look at higher order systems. They are more interesting. Let's add this LC filter here between the machine and the converter. We now want to control the inverter current, the capacitor voltage, and the stator current. And when you look at a representation how a harmonic component created by the converter, how that would interact with the system. So you have here your converter, you have a certain voltage harmonic. This drives a inverter current harmonic. You have the L and the C of the filter. These resistive elements, they're effectively zero. I mean, this is the ohmic resistance of the choke and the electric series resistance, equivalent series resistance of the capacitor. Here you have your terminals of your machine. That would be your stator resistance, also very small in a medium voltage machine. And that's the so-called total leakage inductance. So the inductance that a harmonic at the machine terminals would see. And you see the transfer function from the voltage harmonic at the inverter to the stator current here has this resonance peak. In this case, around 300 Hertz, that's determined by the filter parameters and the leakage reactance. So you can imagine that this is highly undamped. So if we just apply the controller here without knowing about that resonance, we will get huge oscillations. Now, I picked some parameters for the filter. These are typical parameters we would be using. I have a relatively long sampling interval. And if I then plot the current THD versus the switching frequency, and I go for a horizon of 1, you see it works really badly. You need a high, I mean, at least for this case, relatively high switching frequency, and you get a really high current THD at this point here of at the terminals of the machine. horizon of 5 helps a lot, and the horizon of 20 helps even more. So you get here sort of a reduction of almost, factor of 8, 7 to 8. A tremendous improvement. Effectively because the damping is taken into account by your controller. So long horizons really, really help in this case. So you see it here, you have inverter currents, they look awful. Capacitor voltages look okay, and the stator currents are really nice. It's effectively a very, very low current THD. You get the switch positions, very flat harmonic spectrum. You can get very fast torque steps, 3 milliseconds, despite this huge filter. And you sort of get here a bang bang behavior. So the current is high, it gets pushed down and up and then down. And this is really to change the state of energy in the energy storage elements quickly to bring down the torque. So assessment for this long horizon MPC with the filter, sphere decoding exploits the problem structure. So it has relatively little computational burden. The part of the problem is solved offline using this generator matrix, simple control, one loop, no active damping needed. Performance is good. We have low current distortions. We can operate at low switching frequencies. MIMO approach, multiple input, multiple output approach. So excellent transient response. So let's look into this switching frequency. We had seen that the resonance is at 300 Hertz. So a traditional linear controller should operate at least at 900 to 1000 Hertz. Apparent switching frequency of the converter. Whereas here we can operate sort of around 240, 250 Hertz. So that means 120 Hertz per device because we have a 3-level converter. So the switching frequency of each semiconductor device is here 120, 130 Hertz. For the converter, it would be 240 Hertz. So this is below the resonance. And that is a big, big surprise. So this we can really drastically reduce. Now, these are simulation results. I've not run it in the lab. In the lab, there could be surprises. The delays would hurt. The model imperfections could hurt. So take this with a piece of grain of salt. Maybe it's 300 or 400 Hertz we can operate. But I've seen in experimental results this 1000 Hertz being drastically reduced by similar methods. Very good. I will take maybe another 10 minutes if that's okay. We started a bit later, and I would, I mean, if it's not okay, then tell me in the chat. But I want to show you a little bit guidelines and common pitfalls. And that's the last part, and then we can go for questions. One is, how should we choose the cost function? So I would insist that we should penalize the switching effort using this lambda, because when we set lambda to 0, we effectively have a deadbeat behavior. And maybe we can discuss later what deadbeat behavior really means. What it means in this case here is it makes no difference how long your horizon is. You will get exactly the same switching behavior. So if you say I have a switching frequency of 2.3 kilohertz, I'm now here low voltage converter, 2-level with an induction machine, then the current THD is the same, regardless of whether you have a horizon of 1 or a horizon of 10, because I don't penalize switching. So the horizons will not help me. But I also get no improvement with respect to space vector modulation. Rather, in many cases, I'm worse than space vector modulation. And you also see it in this plot down here, as I increase the switching frequency, I reduce the penalty on switching. This is horizon 1, this is horizon 10, so I get a nice reduction in current THD. But if I have no penalty on switching anymore, it doesn't matter. All horizons give me exactly the same switching because I have this deadbeat behavior. So always penalize the switching transitions. Then the tuning. So you can compute a good ratio of penalties between the torque and the flux magnitude. You can try to make your level sets of your cost function for your direct torque and flux control as circular as possible. And you see they are almost circular, because you know that when they're circular, you minimize your harmonic current distortions. And that avoids tuning of penalty rates. So you can analytically compute what is the best penalty on torque and flux terms to get minimum current THD, but still have a direct torque and flux control. And then you can try to avoid the penalty on switching you have up here by putting this into your cost function. So you can track the switching frequency in your cost function. So also no tuning is needed here. Now, when should you use long horizons and when are short horizons good enough? So a two-level low voltage converter, trade-off current THD versus switching frequency, space vector modulation, short horizon, long horizon, you barely see a difference. So maybe you don't need it for these first order systems. Maybe horizon 1 is enough. But if you have an LC filter, the sine filter, then you have a tremendous difference. So here, the same switching frequency can bring down the current THD from 45% or so to something like 5%. It's an order of magnitude. So use the long horizons for systems of a higher order. Then the harmonic spectrum we get is often, a bit unfortunate. If you have a grid-connected converter, you might need to meet harmonic grid codes, let's say IEEE 519 or this IEC 61000-4-2 standard. And particularly strongly are the even order harmonics penalized. And this finite control set MPC just tries to track the currents. It has no knowledge about harmonics. So you will violate them. What you could do is you could try to control the harmonic spectrum using Fourier coefficients. So you have a prediction model that controls the amplitudes of those Fourier coefficients. And you could try to penalize them much more where they are even and much less where they are odd. And you see that you get this sort of shaped spectrum. Now, what sort of a sampling frequency should you use? Fs is the sampling frequency, Fsw is the switching frequency. And I would claim the sampling frequency should at least be 100 times the switching frequency. So limiting the switching frequency by using a low sampling frequency, that's a bad idea. It leads to very high current distortions. And you can see it here. The ratio between sampling and switching frequency is here very low, just 7. This is bad. And you see the THD is actually quite a bit higher than with space vector modulation. But as we increase the sampling frequency, and I also increase the penalty on switching so that we always have the same switching frequency of 4 kilohertz. So each one has 4 kilohertz switching frequency. By doing that, we nicely bring down the current THD. And from a ratio of 100 onwards, there are little benefits anymore. So if you now have 100 or 1,000, doesn't really matter so much. But a ratio of 10 is not a good idea. So, and the explanation is simple. With finite control set MPC, we can only switch at the discrete sampling instances. So you need to finely grid your time axis so that your controller can sample and act at any moment in time, pretty much. If you have a very coarse switching, if you can switch only here and here and here, your controller needs to make a decision. Do I now switch here or do I switch here? And this will be reflected in high current THD. So because of that, when you look into low voltage converters with a couple of kilohertz switching frequency, you might need a couple of 100 hertz sampling frequency. You might want to look into methods beyond finite control set MPC. Let's say you could say, I have a certain modulation cycle, and I allow certain number of switching transitions within this modulation cycle. I want to compute these optimal switching times by minimizing the current ripple. So this would be something like slope-based control, where you formulate a control problem that is very different to finite control set MPC. So you act at these discrete time instances here. So you have a low sampling frequency, but you allow your switching instances to vary smoothly. You're not artificially discretizing them as you do here. Then there is the norm. What sort of norm in the cost function should you use? Should you use the 1 norm or the square 2 norm? And the answer is simple. Don't ever, don't use the 1 norm. It will lead to instability. You see here the trade-off between current THD and switching frequency with the 1 norm. You see that at this point here it ends. You can't increase the penalty on switching and operate here. It's not possible. The explanation is shown here. You lose tracking. Your controller starts to get unstable here. Your currents start running away. And you also see that the THD is really high for the given switching frequency. So we should always use the 2 norm. By doing that, you can guarantee stability and you can guarantee a nice trade-off and a much lower current distortions than with the 1 norm. Stability is a difficult topic. If you really wanted to prove it, you need to prove practical asymptotic stability, simply because you will always be switching. So you will not be able to control your currents to a certain value. You will always have a ripple. You will always need switching. So you can only keep things within certain bounds. So there's literature if you're interested in, but it's mathematically complicated concepts. And then you want to maybe compensate for delays by using your model. So you measure, you know that you have applied certain switch position. You can make a prediction what the states are going to be when you apply your control input. So you measure, you communicate to your controller, you do this state prediction, then you compute your manipulated variable, you send it downwards, downlink, and then you apply it here. But you do that based on the previously sampled state that you have mapped forward. So it is intended for time step k, and it assumes that it's intended for time step k. So you compensate for that delay. And then there's literature on how to implement it. You can do it on an FPGA. So there is a non-recursive sphere decoder using pointers and a few tricks. So you can run the sphere decoder on an FPGA. You can use suboptimal solutions, pre-processing, some projections to really speed up the computation time for certain corner cases. We can discuss these details if you want during the next half an hour. So summary and conclusions, I have 2 slides left, or 3 slides, then I'm done. So we have been talking a lot about these current distortions per switching frequency. I would claim that the product between the two, current THD and switching frequency, is really meaningful and important metric, this constant. You want to get this constant down. So either reduce the current THD or reduce the switching frequency, or both. And then you want to be fast. So you want to have a controller that has a very high dynamic, that can react very quickly to disturbances, simply because bandwidth allows you to compensate for not so good models and for disturbances. You have direct torque control, one extreme, and slow control with optimized pulse patterns, the other extreme. We would like to be here. We would like to have minimum distortions and maximum bandwidth. If you now go for the short horizon, you are a bit better. Long horizons help you. But if you really want to push it to a maximum, you probably want to base it on optimized pulse patterns. So this is this model predictive pulse pattern control that takes a switching pattern and then manipulates the switching instances of the switching pattern in a very dynamic fashion. So finite control set MPC, it is simple. You can use it for almost any control problem. It is very fast, and it works really well for complicated systems. So systems like this LC filters I've shown you, but also machines with saliency, different magnetic behavior in the D and the Q axis. There it works really nicely. What's not so nice is the harmonic spectrum. I mean, you see here you have a lot of noise, a lot of even harmonics. So meeting these grid codes, that's tricky. You need a high sampling frequency, and tuning can be also difficult. Sphere decoding is a good method. You iteratively consider integer solutions. You get a certificate that you have found the optimal solution. So you're not approximating things in any way. You get the optimal solution. It's very efficient, but your problem must be the same at each time step. And you need to have a linear system with integer inputs. This is the last slide. So MPC in general in power electronics has created a lot of interest predominantly in the academic community, but also now in the automotive industry, people are getting interested. It's a potential differentiator and cost saver for industry. And maybe you're surprised by that, but I would say lack of computational power is usually not the main issue. It is usually that you need to get good performance. Computational power just makes it a bit harder to implement it. Commercial benefits, if you want to get it adopted in industry, you need to be able to show how it can save money. So how can you get more power? How can you reduce cost? How can you simplify the commissioning? How can you get lower harmonic distortions to improve the efficiency? This one needs to show to get industry interested. So maybe one would have to look beyond overly simplistic methods, which typically or often don't give you such good performance. Maybe one should look at high performance methods that are a bit more complicated. So challenges are building know-how, productization, that's very time consuming, and to make that happen, you need something that is simple, versatile, and can be applied to the whole range of products. So all types of machines, grid connected, machine connected, and so on. And then having said that, I think what we see right now is sort of the tip of the iceberg, and there's a lot more to be explored. And I mean it in a positive way for people who are even younger than me, that don't think that everything has been done. I think a few things have been done, yes. But if you jump onto the topic, there's a lot you could do down here. There's a lot to be discovered, a lot to be explored. So we are still at a relatively early stage. So with this, I would like to conclude. If you want to read up a bit more, there's a little book I wrote 5 years ago that summarizes most of these concepts. And with this, I would like to thank you for your attention, your patience, for having bared with me, for listening. And now I'm happy to take questions, and we can have a bit of a discussion. Thank you very much. And thanks a lot for having invited me. Thank you.
Participants, if you have any questions, you can unmute your mics and ask, or you can post your questions in the chat box.
Sir, I have a question about this MPC, sir. I just wanted to know as to whether this can be used with all the machines in electrical systems, or is it only used for controlling motors, sir?
No, you can pretty much use it for any system, because the model we have, you can pretty much, I mean, as long as you can model it, you can use it.
Yes. Okay. And so I just want to know as to what are the advantages that MPC offers over the other existing control systems, sir, like for the machines?
I think that's a good question, because one should really ask oneself, what am I going to improve? what is it that is going to be better? Is it just going to be different, or am I actually going to make a difference? I think it depends on the method a bit. I think what I've seen, this finite control set MPC really works well when you have this LC filters. It really works well for filters. And it really works well when you have an imbalance on asymmetry in your system. So when one phase behaves differently to another, when the D-axis is different to the Q-axis. This you can tell this controller relatively easily, and it would be very difficult to explain that to a classic modulator.
Okay, sir. Thank you, sir.
Now, if you just have a simple machine and you want to spin it, then maybe it's simpler. Let's say you have a simulation set up and you just want to quickly see how can you run your system. Then implementing such a one-step predictive control, I mean, effectively this algorithm here, this would take you 2 or 3 hours. No? So it's really quick, and you can get something nicely running.
Okay, sir.
In general, if you really want to push performance, I personally like optimized pulse patterns a lot. So I like to pre-compute the perfect switching sequence and then to modify it online to get feedback.
Yes, sir.
Okay. Then someone is asking about the slides. Yes, I can send you the slides. I make a PDF file out of it. I can send them gladly. Maybe what I can also say is that, I mean, we need control in these corner cases. You know, when you have either fast transients or you operate very close to some physical limits, or you have some faults and you don't want to trip, then you need to have good control. Or when you have a complicated system, so you change the voltage of your converter, that changes a current in an inductor, that changes a voltage across a capacitor, that changes a current in a transformer, and then the transformer has maybe an imbalance because one of the phases at the point of common coupling has a fault. Then it gets interesting. Then you need to have good control. If you're just at steady state and things are turning nicely, it's easy. You can pretty much use anything you want to use.
All right. So as we come to the end of the session, sir, I'd like to thank you so much for giving us such an informative and very impactful session. It was very knowledgeable. So thank you so much. And all of us are definitely looking forward to hear more from you in the future too. And I also like to thank all the students who have come here to attend this session. And I thank you, sir, for giving your time and helping us to learn. So as we come to the end of this session, I'll be sharing the feedback form in the chat box. And I request all the students to fill in the feedback form. And it will be open only for a few minutes. So whoever's present in the meeting, kindly fill the feedback form for the certificates. And the certificates will be shared by 8 p.m. tomorrow. Thank you, everyone. Thank you, sir.
Yeah, thanks a lot for having invited me, and maybe tell me a little bit if it's too technical or if there are 2 or 3 topics you would like to have covered more. I mean, I'm very happy to learn, because this is a more technical talk, so I try to dig a bit more into the details. So maybe you'll say, I want to hear more about applications or some other things.
It was perfect, sir. But if you can, maybe you could add more application based where this can be used, and otherwise it was perfect.
Okay, will do. Thank you.